this computer. Okay, great. So today we will continue our lecture on the second module of time series, and also this is our second last module. So this is the outline of the lecture. The number of slides is a little bit smaller than last time, but the content I think is pretty challenging. So I will try to go through them smoothly and slowly. So we will first have a quick review on the attention mechanism, and then we will talk about what we call the multi-head self-attention. And lastly, we will use these tools to form the transformer model that I would like to mainly discuss today. Okay, so here is kind of like a development flow chart of machine learning algorithms. So we started with, of course, fully connected neural network we go through in the first class. And then, as I mentioned, the machine learning community kind of split into two schools dealing with two different kind of problems. So the part of machine learning that deal with image is called computer vision. And computer vision mainly utilizes a convolutional neural network model. And to solve specific problems, for example, image on a non-flat surface, we use geometric deep learning. To extract the location of object, we use regional CNN. And to deal with a group graph data, we use a graphical convolutional neural network, and also to deal with video, we use spatial temporal. So you see the structure of the computer vision algorithm is kind of scattered. On the other hand, the school that deals with natural language, text or voice or video, so audio, those are what we call the natural language processing. And the development of NLP actually follows kind of a linear trend. So we start from a recurrent neural network model, and then we empowered it to a long short-term memory model, and then we add attention to it, and eventually we move into this region where we use the self-attention and a transformer model to deal with this kind of problem. And actually, what you will find is that the machine learning community actually ended up using this transformer model to also solve a computer vision problem, like analyzing images. So that's something we will cover at the end of this lecture. Okay, so let's first have a quick review on the recurrent neural networks. So when the recurrent unit goes through the current input, what happens is that information from all the previous hidden states and current input are analyzed together in this recurrent units, and the output is produced by a hyperbolic tangent activation function. And the outputs of the hyperbolic tangent function will serve as both what we call an intermediate state output and also the hidden state to the next input. So we keep this serial iteration going until we reach the end, of the waveform or the time series data. And the last hidden state output is the output of the neural network. So there are two important concepts. One is the intermediate hidden state output. The other one is the last hidden state output that we have talked about several times. Give me 1 second. Okay. And then we will do a quick review on attention. So traditional recurrent neural network and long-term memory model utilize only the last hidden states. So we basically throw away all the intermediate hidden states outputs, and that's actually a huge waste on information. So what attention mechanism does is that it wastes all the intermediate hidden state outputs to form a context vector. So the method that is doing this is to calculate a scalar quantity called attention score for each intermediate hidden state outputs, and then it performs a weighted sum of the attention score for all the intermediate hidden state output to produce a context vector. And then the context vector and the last hidden state output is concatenated together to form what we call the layer outputs to the next part of the neural network. Okay, so we also discussed why attention mechanism works. So for example, if we only have seven time index in our time series, which is a waveform here, so attention mechanism will allow the last final hidden state to talk to each of the intermediate hidden states. So if the feature in one hidden state, for example, H3 in this case, is important, then the final hidden state should preserve most of its info, and this would lead to a high attention score of this state as H3 HN. HN is the last hidden state, and H3 is the third intermediate. Is actually the fourth intermediate final hidden state output. And it will also have low attention score on all the other slices. Okay, so we can actually revisit the attention mechanism in a different formulation, which is what I call the QKV formulation. So Q stands for query, and K stands for key, and V stands for values. So this kind of reminiscent idea of, for example, a Python map. Like for example, you send it the query, and the query finds a key, and based on the key, you extract the value. So it's kind of the same idea. So in the case of the attention mechanism, what we do is that we treat the last hidden state outputs, HN, as our query. So that's one that asks for information. And then we treat each of the intermediate hidden state output as our key. So we are querying it. So the last hidden state output talk to the ith intermediate hidden state output, which is a key, to extract the value. And then the value again is also the intermediate hidden state output. So we do a weighted sum on the intermediate hidden state output to extract the attention, the context vector. So attention score is queried by is obtained by query a specific key, and this is equivalent of the calculation of the attention score of F of HI and HN, or you can call it S of HI and HN. That is, the last hidden state output talks to each of the intermediate hidden state output simultaneously. So if a given intermediate hidden state output is important, then the attention score will also be larger, as we mentioned on the last slide. And the output is obtained by multiplying attention score to values. So for example, here I rewrite the output as a softmax of the attention score, which is calculated from the query and keys, and then multiply it to the values, which is also the intermediate hidden state output. So we mentioned that recurrent neural network has many disadvantages. For example, it often lacks long-range correlation. And also it's serial, thus is not parallelizable. So when your recurrent units goes to this, for example, goes to this time index, it has to go through the first two time index first. It's not impossible to calculate each of the time index simultaneously. So that's what we're talking about, non-parallelizable. The natural language processing community has moved in the direction of abandoning RNN because of these regions. But without RNN, both last hidden state output and intermediate hidden state output will be unavailable. We won't have those. We won't have those values to work with on the attention mechanism. So how to deal with that? So the answer is that attention is all you need. This is probably one of the most important papers in the history of NLP, and is now the basis of many important NLP models such as BERT or GPT-3, etc. It's also what's very interesting that it's also caused the trend of naming a machine learning paper with blah blah is all you need. So you can see here I list a whole bunch of all you need paper, which is kind of funny. And I mean you can see its importance by looking at the citation. So it has like 23,000 citations. So it's a really big paper published in 2017. And also, I would recommend a comprehensive review of this paper. If you really want to understand transformer and self-attention into a deep depth, I would recommend you to read this comprehensive review on this paper. Okay, so this is the first part of the lecture. Are there any questions? Okay, if not, we will have maybe like a 2 minute break, and I will get some water. Okay, great. Now is the time to proceed. Okay, so this second sub-module is mainly going to be about self-attention. So as we mentioned in the last sub-module, without recurrent neural network, we don't have we don't have intermediate hidden states or the last hidden state, which means we won't have our queries, keys, and values for the attention mechanism. Therefore, we have to produce them ourselves. So this is actually easier than you thought. So what you do is that you just multiply 3 independent kernel matrices to your inputs values to produce your queries, keys, and values vector. So remember those 3 independent matrices we call multiplies are going to be the kernel of the self-attention layer. So their values change during the training to fulfill the assigned task. And also the kernel is shared by all the time indices. So we multiply the same matrix to the entire waveform. So if we do that, we will have a query, key, and value for every single time index. For example, this waveform, we have 7 time index. So we will have 21 vectors of which is 7 groups of queries, keys, and values. So this operation, again, as I mentioned, this operation is performed to every single time index. And now for each index, we have the 3 representation Q, K, and V. So now for each index I, we perform this calculation. So we calculate this value Z using the softmax of the query times the K divided by this constant number and then times V. So Qi is a query vector of the current time index. For example, let's say if we look at the ith time index for now, well, maybe I will use a number. So for example, if we use the second time index for now, then Qi is going to be Q2. And notice K I label is Kj. So Kj is actually every other time index. So if we are looking at time index 2, then our key is going to be time index 0, 1, 3, 4, 5, 6. So we multiply the current query to every other keys. And then divided as, well, actually not every other key, including itself. So J is going to be 0, 1, 2, 3, 4, 5, 6. So it's going to include every single slice. So you are also calculating the Z score to itself. And so Zj is evaluated for every time index, including the current time index I. And dk is a dimension of data in this time slices. For example, if you're remember we talk about the number of features in the time series. Your time series has like 10 features, then dk is just going to be 10 square root of 10. So the division of square root of dk just for numerical stability. There is no further profound reason. So if you look at this evaluation, you will find it to be very similar to the attention mechanism that we talked about before. So remember, attention mechanism is that you first calculate the attention score via this attention function x, and then you wrap a softmax over it, and then you multiply it to the value. So this is almost the same. So you multiply the query and the key together, and then you use a softmax to produce attention score, and then you multiply it to the values. Okay, so in attention mechanism, the last hidden state's output queries each intermediate hidden state output to produce the attention, to produce a context vector. So the query is performed only once, which is the last hidden state output queries every intermediate hidden state output. So in self-attention, the story is different. The story is a little bit different. So in self-attention, each time index queries all the time index to produce the output. The query is performed n times, where n is the length of the time series. For example, in this time series where we have 7 time indices, we will do this query process 7 times. So each time index is going to be querying all the time index of the entire time series. So in attention mechanism, the attention score is evaluated using certain predefined score function. For example, we talk about we can use a cosine, we can use a cosine distance, we can use a Euclidean distance, or the most commonly used distance is what we call the weight concatenation. We will multiply Q and K with a weight matrix sandwich in between them. So in self-attention, the attention score is directly obtained by multiplying Q and K together. Okay, so actually now I have a question for you guys. So why don't we insert an additional weight kernel as we did for the predefined attention score function, or why don't we use some more fancier operation like a cosine or like a Euclidean distance or something like that? Anyone will try this?
Maybe it's because Q and K matrices are already defined as some complex operation of the input data. There are already those matrices like W, Q, W, K.
Okay, great. Yeah, that's the right answer. So because remember your query and key is already produced by multiplying the kernel function to it. So if you sandwich an additional kernel in between Q and K, then it basically whatever this matrix does can be just absorbed into the WQ and WK, right? So it's a waste of parameter. So that's why we can directly multiply Q and K together instead of having to use some kind of a score function in attention mechanism. So remember, in attention mechanism, the Q and K is produced by the RNN layer. So it really has nothing to do with the attention mechanism itself. It's actually produced by the RNN. That's why we will have to use some kind of score function, and we will have to sandwich an additional weight. So that's the difference between that's one of the difference between self-attention and the traditional attention mechanism. Okay, so the next concept is what we call the multi-head self-attention. So in what we discussed earlier, we mentioned that we can have this pair of kernel matrix WQ, WK, and WV. But instead of only having one group of WQ, WK, and WV, we can actually have many groups of them. So for example, if we have M group of them to look at the time series simultaneously, then each group of WQ, WK, and WV is what we call the head. So head, you can think of it as some kind of, like a probe to probe the time series data. For example, in LHC, we use both a calorimeter and a tracker. So you can think of a calorimeter is a head and a tracker is another head. So the information that produced by each head will operate relatively independently to produce a decision. So if you have, for example, 7 heads, then the output will actually contain 7 of the Z's for each time indices. And then what we do is that we concatenate the 7 Z's together, and then we multiply it by an overall weight matrix to produce the final output, which is of the size, which is still of the size Z. So this is what we call the multi-head self-attention. Okay, so why is multi-head self-attention better than attention mechanism? So the first astonishing feature of MHSA, because it exhibits what we call the global correlation. So basically in MHSA, we allow every time index to talk to every other time index to obtain their correlation. So we no longer need to worry about, oh, the last index doesn't, the last output doesn't contain information from like the very first time index, because now the last hidden state is going to be able to talk to the first time index directly. And also MHSA is simple in terms of computation. So now everything is matrix multiplication and some simple linear algebra, although maybe the concept is a little bit hard to understand, but to the machine is a very easy calculation. And also there's no serial operation. Basically every single time index can be calculated simultaneously because it's just querying all the other time index. There's no like, I have to wait for the output of the previous index to get my current time index. That doesn't exist in MHSA. So because of those very nice properties, MHSA has been used as on many state-of-the-art language models with extremely large training data sets. So this is kind of the development trend of NLP, which is that you use a lot of text, a lot of training samples to train your model, and then you use your model to produce to perform complicated tasks. So that's kind of the idea of BERT and the GPT-3 and etc. Okay, but MHSA is definitely not perfect. So there is one problem. So we mentioned that MHSA resolves all problems of recurrent neural network, but now it has another disadvantage. The order of time series is not properly encoded. So remember that recurrent neural network enforce order information through the serial recurrent operation. Although we don't like it because it's slow, it requires a previous output. But without that, MHSA won't be able to probe the positional information of the time series. So so in order to resolve this, we have to use a technique called positional encoding. So positional encoding is an important technique in MHSA paper to resolve this issue. So if you are planning to use a CNN to analyze time series, because as I mentioned, CNN also does not enforce order information. So you will also need to add this positional encoding to your data. Okay, so what is a positional encoding? So positional encoding need to satisfy two features. So the first feature is called absolute position. So the second feature is a relative position. So let's look at this sentence again. Love looks not with the eyes, but with the mind, and therefore is winged Cupid painted blind. So the idea of absolute position is that we will know that eyes is the 6th word in the sentence, and mind is the 10th word in the sentence. So those positions are absolute, meaning if you have a completely different sentence, for example, no one knows something better than me, then you will also know the 6th word in this word. So, so you have to enforce this absolute position in a time series model. So the other is what we call the relative position. So the word mind is 4 words behind eyes, just like the word the is 4 words behind love. So you need to understand the distance between 2 words. So the attention is all you need paper use a very smart way to do this positional encoding. So the idea that the position of each time index ti is encoded using a d-dimensional vector. So you're not just using one number to encode the position, but using a vector. So the d-dimensional vector contains alternative sine and cosine function with different frequencies. So we will give a relatively vivid example about why it actually works. So the detail of this PE algorithm is quite mathematically heavy, so I decided not to show it here, but I will give you a very good simplified example about why it works. So for example, if you are trying to represent a number from 0 to 15 using a binary number representation, using a 4-digit binary number representation. So you can see 0, of course, is 0, 0, 0, 0, 1 is 0, 0, 0, 1, and 2 is 0, 0, 1, 0, and etc. So we can do this all the way to 15. So that's what you do if you look at the horizontal direction. But if you look at the vertical direction, you will see that in the first digits here, as I circled using my mouse, you can see it's actually oscillating between 0 and 1, 0, 1, 0, 1, 0, 1, all the way to 15. And then on the second digit, you see is 0, 0, 1, 1, 0, 0, 1, 1. You see the pattern is also alternating, but it's with a smaller frequency. Here it alternates between every 2 numbers. Now it oscillates between every 4 numbers. And similarly, if you observe the third column, you will see it has 0, 0, 0, 0, 1, 1, 1, 1, and then 0, 0, 0, 0, 1, 1, 1. So now it's oscillating with every eight numbers. And lastly, the fourth digit oscillates with every 16th numbers. So basically, this idea is that if you have some function that oscillate under different frequencies, you can actually use that to represent a continuous varying number series. So in the machine learning case, we don't usually use binary number to represent information because it's kind of a waste of space. So basically, the idea is to convert this into a float point space representation. And then we will get the positional encoding in sine and cosine that we talk about. remember we have the sine and cosine oscillating at different frequencies. You can also look at this plot where you see basically this plot is just the sine and cosine version of this representation, where the x-axis represents the position we will want to encode, and the y-axis is a d-dimensional vector that we use to represent this position. So you can see in the first dimension is oscillating pretty vastly, and then on the second dimension it oscillates less frequently, and then all the way as you move to the right on this plot, you see it oscillates less and less frequent until here. The first oscillation is actually beyond the scope of this plot, so you only see this uniform feature. So this positional encoding vector of the d dimension is just directly added upon our time series as input of the neural network. Okay, so this is actually not the only way to do positional encoding. Remember, we mentioned several times that the zen of machine learning is that you learn everything that cannot be figured out by hand. So positional encoding is also something that's relatively complicated. So we can also use this learned positional encoding mechanism. So what I mean by learn is that we set up a trainable kernel and we let it figure out its value during the training process. So since positional encoding is tricky for MHSA model, we can also ask the neural network to learn the positional encoding by itself. So this approach is actually adopted in the BERT model I mentioned earlier. So what we do is that we modify the original MHSA so that it does not only query the key, but also query the positional encoding. So basically the idea is that you have the query times the key, and also you have the query times the R, where R is again a trainable kernel that we design, which contains the positional encoding information. Okay, so the last thing I would like to cover in this submodule is what we call the residual connection. So residual connection is a simple yet powerful technique to avoid gradient vanishing. So the idea of gradient vanishing is that if a neural network is too deep, the gradient might not be able to propagate into some of the parameters, and those parameters will never be updated. So that's what we call the gradient vanishing. So gradient vanishing is a natural consequence of derivative operation. For example, it's not surprising to say if you take a derivative for arbitrary function, it's not too surprising to see that the derivative goes to 0. And as we mentioned in the first lecture, your parameter is updated by calculating the gradient, which is a derivative with respect to these parameters. So if your derivative is 0, that means this parameter is not going to be updated. Its value is just going to stay there. However, what you can do is that if you add the input x to the function fx like this, now you redefine your new function as fx plus x, then if you take a derivative to it, it's never going to be 0. It's at least going to be 1, right? Because dx equals 1. So the idea of residual connection is based on this idea. You have some neural network function fx here, and what you do is that on the outputs, you add x to your function fx, and then you feed it into the next layer. So residual connection, another advantage of residual connection is that it allows information to flow directly from input to the output, because you are directly adding your input to your output in this case. So for example, the positional encoding is added to x. So it's added to the input before we feed it into the multi-head self-attention layer. So it can easily get lost in a deep multi-head self-attention neural network. But the MHSA module actually contains what we describe as a residual connection, so which allows the positional encoding information to directly flow to the output. And thus, we can utilize this information for the purpose of our model design. Okay, so this is again, this is a second submodule. I think some of the content could be pretty confusing, so I didn't really leave any question here. So if anyone have question, please feel free to ask. Okay, great. So we'll take another 2 minutes break before we go to the last submodule. Okay, so let's proceed. Okay, so the last module I would like to utilize what we have introduced in the previous submodule to form what we call the transformer model. So first we will start with what we call the sequence to sequence model. So this actually falls in the scope of NLP and machine translation. So it's not necessarily useful for time series, but I think it's still useful to discuss what it is. So first of all, we discussed about this encoder-decoder approach in the convolutional neural network case, where so the idea is that you use a series of CNN layers to encode your encode your input image into a vector, which is what we call the latent space representation, and then you use a series of deconvolution layer to convert this latent space representation back to the original image. And when training, you are training to minimize the MSE distance, the mean square error distance between your input image and your reconstructed image. So this encoder-decoder approach is easier to build and it works well on time series. If you are trying to do this in, for example, machine translation approach, for example, you can feed in English and you train it to translate it toward Germany, and then you use kind of a regression loss. For example, mean square error we talk about, or you can use L1. So unfortunately, this actually doesn't work very well on the language training because I think the deep underlying reason is that neural network is better at classification than regression. So in order to resolve this, we use what we call the sequence to sequence approach. So this works better for the language model. So the idea is that in the training, you feed in both English and German sentence together. And then you produce something called S between the English and the German sentence. And so what happens is that it's going to store the English German words into their dictionaries and then treats. So remember we talked about this word embedding idea. So the idea is to store each English and German word into a dictionary and then treat them as a one-hot embedding. So like 0, 1, 0, 0, 0, 0, 0, like that. So the idea is for every given English word, for example, here I have a he, I want to use the input and the memory to ask the neural network to classify what word I should use. So in Germany is a word I don't know how to pronounce that, to be honest. So in this case, we are converting a regression problem to a classification problem. And it has been shown that this sequence to sequence model works much better on machine translation compared to like the encoder-decoder approach that we discussed earlier. So, okay, finally, we will be able to introduce what we call the transformer. So transformer is basically a sequence to sequence version of the multi-head self-attention network. So let's go through the structure of this network. So first we have the inputs which undergo some kind of embedding that we talked about. And then we add positional encoding to the inputs. And then we feed it into many multi-head self-attention block to produce what we call the memory, as we showed in the last slides. So each MHSA block contains MHSA layers plus a fully connected layers plus a normalization layer plus the residual connection, as we discussed earlier. And the outputs, as we mentioned, in a sequence-to-sequence model, we feed in the input and output simultaneously to produce the memory. So the output is also analyzed by many MHSA blocks. So, and then the output and memory are jointly fed to another MHSA block, followed by fully connected layer to produce the classification decision, which is a vector. So if you have done the earlier homework, you know that we produce a vector for every we produce a vector as the output of the neural network, and the vector after taking the softmax is represent the probability of each image or word falling into this class. So again, here I skip a lot of technical details such as the end of sentence tokens, teachers enforcing masking, etc., because those are really natural language processing specific, and you don't really need it for time series. So if you are interested in this, I recommend you to read the blog on slide 9, as I mentioned. I'm also going to list this on the course website. Okay, lastly, we will talk about something called a vision transformer. So this is a very interesting idea. So it was first proposed in this paper, and transformer has been transformer has some very nice properties which makes it suitable for image data as well. So for example, we mentioned about the global awareness, and we talk about that it's very important to find the global awareness in image data, and transformer naturally enforce global correlation, which will give rise to the global awareness. And it's also very strong at picking up correlations. And lastly, it has this feature called attention score, which is naturally interpretable, which can help us understanding which part of the image it's looking at. So in the second half of last year, 2020, applying transformer to image data had been a very, very hot research topic. This way we have this model called vision transformer that was born actually on the second half of last year. So what we do is that, for example, here we have an image of a church or a library. I'm actually not sure what it is. So what we do is that we split the image into different patches. So you see this contains the main building, the top of the main building. This contains a tower. This contains some bush. This contains a light. And then what we do is that we flatten each patch into just a 1D vector, and then we use the linear projection. So that is multiplying it to a matrix to convert it to what we call embedding representation. Here we have actually, you see we have 9 patches. So we feed it into this vector, and we also add an additional 10th patch, which is what we call the class embedding. So if you remember the nature of the multi-head self-attention algorithm, so basically every patch, every input will be able to query every other output. So if we add an additional class embedding, if you add another class embedding as our input, then this class embedding is also able to query every other output to extract the useful information. That's why vision transformer actually works. And we add conditional encoding to this linear projection. As you can see, it shows in numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 9. So that's the positional encoding. So the author actually tried both 1D PE and 2D PE, but it did not find much performance difference. So it looks like the 1D positional encoding is performing good enough for the purpose of the vision transformer. And then what we do is that we will feed it into the transformer layer to perform the multi-head self-attention operation. And then we pull out the class embedding information to a fully connected neural network to perform the classification decision. So one of the advantages, as I mentioned, for the vision transformer is that we can look at the attention score observation transformer to determine which part of the neural network is looking at to make the classification decision. So based on the plot on the right, you can see the neural network is actually correctly attending the correct part of the image to make the classification decision. For example, when it's classifying a dog, it's actually attending the body of the dog, but not the grass around it or the tree in the back. When it's looking at, when it's trying to classify a plane, it's actually looking at the plane, not the cloud in the back or not the sky. Well, when it's trying to classify a snake, it's actually worse. So the snake doesn't actually get much high attention, but it still gets some attention. So this heat map style plot, is extremely useful in computer vision tasks, and it can also be directly read out from in the vision transformer by just pulling out the attention score. So if you want to make such a plot in convolutional neural network, you actually need additional network interpretability tools such as GradCam or guided BP. So that's one of the advantages of the vision transformer. So some other advantages that the author has observed that vision transformer is less susceptible to what we call the inductive bias. So for example, if your image is not flat or if your image is flipped, the vision transformers can still capture its feature, while if you use a traditional convolutional neural network, the feature might not be correctly accounted for. Okay, so this is all I would like to go through in this course, in this module. So we review the attention mechanism and recurrent neural network. And we also revisit RNN as a QKV formulation. And then we introduce the multi-head self-attention modules, where we discuss about self-attention as the same QKV formulation. And you can see it's actually analogous to the attention mechanism we discussed earlier. And then we also introduce multi-head self-attention. And we also introduce positional encoding and residual connection. And then we talk about sequence-to-sequence model and how to form this as a transformer. And lastly, we discuss about the vision transformer technique that has been very recently developed. Okay, great. So this is everything for this course. Before I end, I would actually kindly ask everyone to turn on your camera and so that I can take a course picture. Okay, great. I'm gonna take the picture now. All right, okay, Lex might just turn on, so let me do it again. Okay, great. Now the picture is taken. Thank you for your patience. And okay, so I think, I guess the course material I discussed today is a little bit involved. So I haven't heard too much questions actually. Does anyone would like to ask questions at the end?
So could you please say more about the memory? I did not get how do you form memory?
Oh, sure. So basically, the idea of memory actually comes from this this idea of sequence-to-sequence model. So the idea of memory is that you feed in during the training stage, you feed in both the sentence in English and German together into this encoder-decoder approach. So actually, it may be easier to visualize this from the transformer model idea. So when you feed in actually both the input and output to produce a joint vector, and then you feed this to jointly produce a vector. So this vector is what we call the memory. So if you are trying to use it to actually perform the machine translation, then what you do is that you feed in the English word. You feed in the English word, and then you feed in a start token. So this start token will kind of trigger the translation, and it tell you, oh, now I have the English word, and I would look like what is the first German word. So this first German word in this case is this word. So the decision is jointly made by analyzing the memory, which is extracted from the English sentence and the first token of the sentence.
So if I just use a layman understanding of memory, that would be that it is something I can use to analyze new data when I have the new data. So from that point of view, I feel like that the memory should be used as kind of input together with the new data.
Well, I
to
mean,
get
that
the final result.
you are actually correct. When you do the machine translation, the memory is the input, but the memory is extracted from the encoded English sentence. So what we do is that we encode our English sentence into some kind of representation, and then we want to. So basically, when you do your translation, it's kind of the same story, right? You hear a sentence, and then you remember it in your head, or you remember it in your memory, and then you speak it out using a different language. That's what we do in translation. So the idea of the sequence-to-sequence model is similar. You remember this sentence as a memory, and then you take in a token. So this token tells you, now I should start translating. And then based on the memory, I will spit out my first Germany word. But this process is done using a classification. So that's the beauty of this sequence-to-sequence model. It's not done using regression, because regression is really hard in a machine translation test.
Okay, thank you. Another thing is that why do we do a shift to the right?
Okay, so the reason of why do we do a shift to the right is because you need a start token when you want to translate. Basically, the idea is that after you remember the entire English sentence, you need to give it input to tell you, oh, now I want to start. You cannot give it the first Germany out input, right? Because you don't know what it is. You want to translate. But if you give it a token, so here it uses a no, but you can use arbitrary number. Give it a number -1 to say, okay, if I see a number -1, I know I should start translating. So that's why it has this shifted 1 unit to the right. So when you have the memory and you see this token, it know, oh, now I should spit out the first word, and the first word is this ER in Germany. Yeah.
Okay, thank you. So the final question is that in your top picture, where you have input image and then you reconstruct the image, and you have the encoder and decoder. So in this particular example, I'm not talking about the language translation. In this particular example, does the decoding use the same weight matrix? You just use it the other way around?
No, it's a different set of weight matrix. So the convolution and deconvolution has different weight matrix. So I mean, if you think about the mathematical example, then these two matrices should be kind of the inverse of each other, right? Mathematically speaking. So they are definitely not the same weight matrix. They are different, and they are
related. That's my point. They're related.
Yeah, they are related. Yes.
And then you have to use some mathematical way to transform it to the decode. Which means that all the weight numbers will be reused. Is that right?
Well, calculating matrix inverse is extremely hard. You may have already know. So usually what we do is that we don't just use a mathematical operation to do this, but we let the neural network learn the proper value.
Okay.
Yeah.
So then the last would be to compare your reconstructed image with the input image.
Exactly. Yes.
If they're similar, then you have a high score. If they're not similar, you have low score.
Exactly. Yes. And the comparison is done by the mean square error. So just takes a Euclidean distance between the two images.
Okay. Thank you.
Okay, great. Is there any other questions? Okay, if not, let me stop.